Hi everyone, I'm here to talk about the learning theory I chose, mathematical problem solving. So I made a Google slideshow and I'm going to go through it with you through this screencast. Alright, so I chose mathematical problem solving. It is a learning theory created by Alan Schoenfield. And one of the things I noticed and I first wanted to have was, why have mathematical problem solving? And then I found this quote that I thought was perfect and related to what mathematical problem solving was. So a teacher of mathematics has a great opportunity. If he fills his allotted time with drilling his students with routine operations, he kills their interest, hampers their intellectual development, and misuses his opportunity. But if he challenges the curiosity of his students by setting them problems proportionate to their knowledge and helps them to solve their problems with stimulating questions, he may give them a taste for and some means of independent thinking. I thought this quote was really important because so many times mathematics is very routine. A lot of teachers just give worksheets, they have them practice problems, and a lot of students don't like math. I get it all the time. I hate math. And I noticed that, when you kind of engage the students with different types of problem solving, giving them opportunities to collaborate with others, not just a straightforward procedure, students start to be more engaged and they might actually find a little more interest in mathematics. So this quote by G. Palia was like a perfect introduction to what mathematical problem solving is. So the definition that I found is mathematical problem solving is engaging in a task where the solution method is not known in advance. In order to find a solution, a student must draw on their knowledge, and through this process will often develop new understandings. So the important thing with giving a mathematical problem solving, problem to the students is there's just not one direct way of knowing what to do. You give them a problem and they should not know exactly what to do, how to do it right away. And they need to, think upon different skills that they've learned, different procedures that they learn, maybe discuss it with the teacher, with students, and then know kind of to go from there. Mathematical problem solving is super important to developing mathematical knowledge at all levels. So you can start mathematical problem solving as early as elementary school, and it continues on throughout college level mathematics. So the primary purpose of mathematical problem solving is for instructors to teach students how to think. You want them to further their knowledge with mathematics by having them question or probe, having them get to the mathematical heart of the matter. In other words, how is this relevant? How is this real world? What connections can I make with this? And for them to employ ideas rather than simply regurgitate them. So you're not just having them do mathematical facts, back and forth. Maybe you're giving them a word problem or something different. So it's the instructor's job to actively ask questions that, are encouraging students to participate in discussions, solving and presenting their thought process and solutions. It should not be a quick, drill and routine problem. It needs to be something else. So mathematical problem solving is everywhere in your standards. So the National Council of Teachers of Mathematics standards from 2000 have these 4 standards that are related directly to mathematical problem solving. So first, all institutions should be able to have their students build new mathematical knowledge through problem solving, solve problems that arise in mathematics and in other contexts, apply and adapt a variety of appropriate strategies to solve problems, and then in the end be able to reflect on their processes, talk about it, explain it, and build discussions. So Schoenfield tells us that there's 4 categories that students must know in order to be successful in mathematics. I'm going to explain them more in the further slides. But the first is resources, heuristics, control, and beliefs. So talking about resources. Resources is all of the knowledge of mathematics that the students learned. This is typically taught through a teacher or through a textbook, through practice, through examples. So kind of looking on both sides of the spectrum, I looked at elementary examples as well as secondary, but some procedures that students learn in the elementary level are regrouping, being able to compare fractions, whether it's a mixed number or improper fractions. You're measuring with different tools like a ruler, being able to create a bar graph, and the last one, I'm not seeing it here. Oh, long division. Those are all step-by-step procedures that elementary school teach the students. On the other hand, for secondary examples, we have factoring, solving an equation, graphing a function, simplifying a rational expression, finding area or volume. I'm going back to this PEMDAS idea that we teach the students so much. These are all procedures you teach them and that are going to help them in whatever problem that you give them. Heuristics are, the strategies used to help solving more complicated problems. So we teach them, I found this picture that kind of show all the different things. We teach them when they see like a longer problem to draw a picture that represent the problem. Make a list. Guess and check is really common in the elementary levels for teaching. Have them create a number sentence, break it down and maybe solve something a little more simpler, make a model, so whether that's a chart or a graph, relating it to real world, act it out, identify a pattern, or work backwards. Control is when the students start to decide when and what resources and strategies to use when solving a problem. So for example, if I give the students a word problem that Leah's at the store, Leah wants to buy 3 candy bars that cost $1.37 each, and a gallon of milk for $2.41. She only has $10. Does she have enough money to buy the items? If so, how much will she have left over? So kind of the control aspects is the students deciding, okay, what do I do with this information? So maybe the first thing that they do is highlight the important information. They highlight the cost of each candy bar and draw a picture if needed. They highlight how much money she has. Then they decide to use operations of adding decimals to determine the total cost of items. So they know they're going to have to add $1.37 to itself 3 times, add it to the $2.41 milk. They got to use their operations of adding and how to add decimals. Then they need to know, okay, well now that's not what the question's asking. The question asking is, does she have enough money? So if she does, how much will she have left over? So they got to use the operation of subtracting decimals, which brings up the idea of regrouping to determine how much change she has left over. Then after they do all this work, okay, they use logical reasoning to make sure the answer makes sense. If they're getting like a crazy number that's not related to money at all, then they did something wrong. And then kind of the last strategy that we teach our students with word problems is to make sure you answer all parts of the question. So first answering, does she have enough money to buy items? So you would say, yes, she has enough money, and she has however much money she has left over, making sure to label it with the correct units. Beliefs is then finding that connection and relevance to the problem and connecting it to whether it's your background knowledge that you already know, real-world applications, previously learned concepts. So for example, I'm thinking of the connections whenever we see money, we're going to relate it to our decimals and what we know about decimals. Geometry can easily be related to so many real-world examples. A sphere is related to a basketball. A rectangular prism is related to a building. So we're relating those geometry ideas to real life things that you can physically see. Relating your exponential functions that you learn in Algebra 2 to different ideas about banking and interest. And connecting, the whole idea of factoring is, division. It's the main idea of division. GCF, your greatest common factor, and different methods such as the AC method. So Schoenfeld gives an example of his theory connected to a geometry class that he's teaching at the college level. So the problem is, given 2 intersecting straight lines and a point P marked on one of them, show how to construct a circle that is tangent to both lines and has a point P as its point of tangency to the lines. So this is a problem that you don't necessarily know the answer right away. You can't just know exactly what to do. So you first want to think of your resources. So the resources would be the teacher teaching constructions in previous lessons, talking about what perpendicular lines are, what tangency means, and using, notes in previous examples to help figure this out. Then the heuristic idea is to be able to construct a sketch to better understand what the picture is going on. So you're going to show a circle, you're going to show a couple points, and then what is it supposed to look like? Control is actually deciding, okay, I'm going to need a compass and a protractor and maybe a straight edge to actually construct an actual circle and its line segments. And then the belief is knowing what the answer should look like. The answer is not going to be a number. The answer is going to be a drawing. It's going to be shown through a construction as opposed to, some algebraic expression or derived through numbers. So overall, I found a lot of resources. I used mathematical problem-solving techniques by Hall to give me a lot about that picture. It was actually really important to me. The standards from the NCTM, Schoenfeld had a lot of books that he wrote about his theory, and I was actually able to access a lot of them. They were given as PDFs. I used Canisius's website to figure them out, and a lot of times I just typed in Schoenfeld mathematical problem solving, and a ton of PDFs came up for me. And then this article by Schwantz to help me, further this presentation. So I hope you guys learned a lot from this. It's definitely a connection to me as I teach Algebra 2. It's kind of given me a new way to think about how I'm supposed to teach, and I'm not just going to give them a, lower order problem where they're just solving a problem. I'm going to relate it to mathematical problem solving, giving them something a little more challenging, which is also helpful when we talk about Bloom's taxonomy. Giving drills of problems is very lower order thinking, but Schoenfeld and I think would believe that, in Bloom's higher order thinking skills, reaching those higher levels, giving them more to think about. I hope you enjoyed this presentation, and you will see my discussion questions attached to this.